Imagine trying to build a multiplayer virtual world where every player's camera sees something completely consistent, even when they look at the same scene from different angles. Traditional video models generate frames from a single perspective, which quickly breaks down when multiple agents interact. This paper introduces WorldWeaver, a streaming video diffusion model that uses explicit world state registers to maintain a unified, evolving representation of the environment shared across all agents. A fundamental limitation of current video generation pipelines is their reliance on raw pixel history to remember the state of the world. When models generate video chunk by chunk, they must reinfer the underlying 3D geometry and object positions at every step. In multi-agent settings, this egocentric approach leads to massive mismatches between what different players see, causing objects to drift or disappear when they are out of view. To solve the consistency problem, WorldWeaver introduces a set of learnable tokens that act as a shared memory bank for the entire simulation. These world state registers live alongside visual frame tokens in the transformer. Instead of discarding history or relying on raw pixels, the model dynamically updates these registers after each generated chunk, carrying forward a compact, abstract representation of the world state across rollout steps. For these memory tokens to be truly useful, they must be grounded in actual physical and semantic properties of the environment. During training, auxiliary decoders force the registers to predict three things: individual agent statistics like position and velocity, a global bird's-eye view map for spatial geometry, and descriptive scene text for high-level semantics. Crucially, these decoders are discarded at inference time, meaning there is zero extra computational cost during rollout. A key architectural challenge is that generating raw pixels and updating abstract world states are highly conflicting objectives for a single neural network. To prevent these tasks from competing, the authors propose a mixture of transformers design. This architecture uses separate, dedicated parameter branches to process the register tokens and the frame tokens, while still allowing them to interact globally through a shared attention mechanism. Training a streaming world model requires a careful progression from perfect teacher-guided learning to independent generation. First, the model undergoes bidirectional training to learn cross-agent consistency. Next, it transitions to causal training with register supervision. Finally, in the self-forcing stage, the model is trained on its own generated, noisy rollouts, exposing it to register drift and teaching it how to correct errors over long horizons. When put to the test in complex multi-agent Minecraft environments, WorldWeaver shows a dramatic leap in performance. It achieves a world score of 105.1, far surpassing previous state-of-the-art models. The qualitative results show that even when agents move independently, their generated views remain perfectly synchronized, and the decoded registers accurately track their coordinates, bird's-eye maps, and textual descriptions over time. Despite these impressive capabilities, scaling this approach to real-world videos presents some unique challenges. Obtaining precise agent coordinates and bird's-eye views is easy in a simulator like Minecraft, but highly complex for real-world footage. Although the authors successfully demonstrated a semi-supervised extension using unlabeled data, future work must focus on learning these registers from raw, unannotated video streams.